Hello. So today we continue our quest in trying to understand rather simple circuits using Radioshack electronic labs, various electronic labs. In this case, the 130 and 1 electronic lab. So this is experiment 71, basic increase in DC voltage. In other words, it's DC amplification using an op-amp. If you look here, you have the op-amp. And here it's got a feedback loop on the inverting input. You can see the feedback loop, and this is the RI. I'll show you I'll show you in a minute. And the input DC to amplify is going to go on this side, the plus input, which is the non-inverting input, and that's the output at 67. So the idea is that to light up those two LEDs, you need at least 3 volts. So that's why you have a switch here. We're gonna supply different values for the input voltage and see the effect on the LED. And I'm going to do that right now, going to the bench, and we're going to go back to this later to explain how the op-amp works and this circuit in particular. How the op-amp works in this particular case, and we're going to of course explain how the circuit works. So let's go to the bench. Okay, so switch on B. This is the LED 1, LED 2. Nothing happens because there's not enough output voltage. You need 3 volts to get the LEDs to light up. So this is not happening. When you switch from B to A, they light up, meaning that you have more than 3 volts at the output of the op-amp. Now in the experiment, what they want you to do is go back to B and press the key here. So I press the key, it changes the amplification factor. So when you press the key, they light up. And if you want, you can go back to A. So A, we know it lights up, but if you press the key, because the amplification factor is greater, the LEDs are going to be lit more brightly. So let's make sure of that. So press the key. Yes, I don't know if you can see that, but they are a little bit brighter. Okay, so that's the circuit. And this is the 130 in 1, and as you can see, I mean, it's a simple circuit, but you still have lots of wires. Anyway, let's move on. Okay, so this is actually the circuit the sub-circuit that's in the circuit we are studying. So this is your op-amp. You have the input voltage that comes here. In our case, it's not a sine wave, it's just a DC voltage. So this is the input side. So this is the non-inverting input. This is on the minus input, which is the inverting input. And you have, as I said, the RI, and you have the feedback loop. And that connects to ground. So the feedback loop connects the output back to the input. The purpose of that feedback loop is to reduce the amplification gain, if you will, because if you don't control it, then it's very, very high, and the op-amp is completely useless because it always goes in saturation as soon as you have a difference here between the two voltages at the input. So AV amplification is equal to RF over RI plus 1. And this we don't really care, but that's the input resistance looking in the whole thing. So it's infinity. So that's the non-inverting amp. And what so the output in our case, so you have amplification, so instead of being here, you end up with being there. And what I want to say is that whenever you have a feedback loop, the two voltages at the input are going to be pretty much the same. So if V in at the plus side is, let's say, 1.5 volts, here the voltage here is automatically going to be also 1.5 volts. It has to be, otherwise you would not be able to control the gain. So because if you have 1.5 and on the minus you have 1.48, you're going to have 10,000 times the difference, and it's going to be out of control. So the feedback loop kind of regulates this here so that the two voltages are about the same. And you're going to see that in the circuit that we are studying. You're going to see that no matter what you put here, the voltage here is going to be the same. Okay, so let's move on. Okay, so that's a cool circuit. Okay, let's look at 63 and 70. That's the supply voltage. So you supply, what, 9 volts? Positive, and the negative is just ground. So this 69, the positive input, is the input. I'm gonna give the input voltage. So that's the input voltage that we want to amplify, and it's DC. 68 is the inverting input, and you can see that you have, if you compare with my previous slide, this is basically the RI, and this one is the RF. This is the feedback loop, and as you can see, it goes to ground. And here there's a what they do, they put a key, so that if you press the key in, you're gonna reduce that whole resistance. Those are two resistors in parallel, and that affects the amplification factor. So remember, AV is equal to RF over RI. So if you put the two resistors in parallel, the resistance is going to be lower. I think probably around 32K here. Okay, so AV equal RF over RI plus 1. Okay, so if you put the switch on A, okay, first switch, I think the first thing is switch on B, if I'm not mistaken. Hold on, let me see what I did. Switch on B. So let's assume the switch is on B, not A. If the switch is on B, what is V68 here? So V68 is 0.8 volts. Why is that? And I'll explain to you right now. It's because of the V69. V68, okay, what is V69 when the switch is on B? As you can see, you have 1.5 volts, and then you have a voltage divider here, the 10K and the 10K. So you know that here you have 0.75 volts. So V69 is 0.75 volts. Let me check. I get 0.8. 0.8. Correct. So now, because of that, because the two voltages at the inputs must be the same, V69 is 0.8, then V68 has to be 0.8. And this is actually what happens. When I measure, V69 is 0.8. And what is the output? What is the output? Well, the output is the formula, and I think they put it here on the side. Okay, you have that 0.75, and then you have the amplification factor, which is R1 over R2 plus 1, and it gives you a V out at 2.4 volt. So they're saying that V67 is 2.4. Let me check what I get. I get 2.5, correct. And for the two LEDs to light up, you need 3 volts. So they will not light up. They will not light up. So now what happens when the switch goes to A? When the switch goes to A, you have 1.5 volts and you bypass the voltage divider, so you have 1.5 here, V69. Let's check. V69, I got 1.6. So now this has to be also 1.6. And again, you can compute the voltage at the output using the formula, and you would get, and I measured it, V67 is equal to 5 volts. And this time the LEDs light up because it's more than 3 volts. So in the experiment, they change, if you press the key, it changes the amplification factor. So when the switch is on B, the LEDs are going to light up, and when the switch is on A, the LEDs are going to light up more than when the key was not pressed. But I'm not going to go into that because it doesn't add anything. So I think I'm going to stop here, and I think this one is an excellent circuit to study. It's very good for amplification. Right now it's just DC, but AC is pretty much the same idea. Okay, so you can amplify DC or AC. So if you understand how DC gets amplified, you understand how AC, like an audio signal, is going to be amplified. Okay, so I'm going to stop here and I'll see you around. Bye.